For 70 years, stealth was America's ultimate trump card in the Pacific. A bomber that radar couldn't find, a fighter that simply wasn't there. An entire military doctrine built on the assumption that invisibility was permanent. Now, two things are happening simultaneously that the Pentagon did not expect to happen at the same time. China is mass-producing a detection device designed to make stealth visible, and the United States is racing to harden its own quantum sensors for actual deployment on actual military platforms. Like and subscribe, because the question nobody in Beijing or Washington wants to answer out loud is whether the era of uncontested stealth is already ending. Let's start with what quantum radar actually is and why it matters more than anything else currently happening in Pacific military technology. Every stealth aircraft ever built, from the F-117 shot down over Serbia in 1999 to the F-22 Raptor and the B-21 Raider flying today, defeats conventional radar by the same basic mechanism. The aircraft's shape and surface coatings absorb and deflect the radio waves that traditional radar transmits, returning so little signal that the receiver on the other end effectively sees nothing. That's the whole game. Minimize the return. Disappear into the noise. Quantum radar breaks that game entirely by not playing it. Instead of transmitting radio waves and waiting for their reflection, a quantum radar system generates pairs of entangled photons, quantum-linked particles whose states are correlated regardless of the distance between them, and sends one photon toward a target while keeping the other as a reference. When the transmitted photon reflects back, even the smallest possible return can be compared against its entangled twin, filtering out noise with a precision that no conventional signal processing technique can match. The aircraft that absorbed or scattered the radio wave hasn't absorbed the entangled photon. It still returns something, and the quantum correlation between transmitted and retained photon makes that something detectable even when it's far too faint for any classical radar to notice. This isn't magic. It's physics, specifically the principle that entangled particles, once created as a correlated pair, carry information about their shared origin that cannot be replicated by noise or interference. When a conventional radar system tries to detect a stealth aircraft, the tiny return signal drowns in the background noise of electromagnetic interference from the atmosphere, from nearby equipment, from thermal radiation. Classical signal processing has fundamental limits on how much of that noise it can filter, because it doesn't know which incoming signals are genuine reflections and which are noise. A quantum system comparing the return against an entangled reference does know, because the correlation between the entangled pair provides a kind of verification signature that noise cannot possess. The signal isn't louder. It's verified in a way that noise cannot be, which amounts to the same practical outcome. The target that was invisible is now, at least in principle, detectable. Read that again slowly. A stealth aircraft isn't invisible to quantum detection in the same way it's invisible to conventional radar. It's just quieter. And the entire point of quantum illumination is that quiet is no longer a sufficient defense against a sensor system that can detect individual photons correlated against an entangled reference. Now here's where it gets disturbing for decades of US military planning. In October 2025, Chinese state media and the South China Morning Post confirmed that China had begun mass production of what it called a photon catcher, a 4-channel single photon detector developed by the Quantum Information Engineering Technology Research Center in Anhui Province. This isn't a laboratory curiosity. China's state media explicitly described it as a component intended for quantum radar applications capable of detecting the faint photon reflections that stealth aircraft surfaces return. The device represents the first commercially viable component of a quantum detection chain being produced at manufacturing scale rather than assembled one prototype at a time by research physicists in a university basement. The framing of this announcement matters as much as its content. China's People's Liberation Army Air Force has spent years being systematically outmatched in stealth capability. The U.S. operates the F-22 and THE F-35 at scale. The B-21 Raider is entering service. The B-2 Spirit, still flying, represents decades of investment in aircraft that Chinese conventional radar systems have significant difficulty tracking. Beijing has publicly acknowledged this gap, and its response has been a layered counter-stealth architecture: cognitive radar, quantum radar, microwave photon radar, and AI-integrated detection networks simultaneously, not betting everything on one approach, but building the capability to combine multiple sensing modalities into a system where each covers the gaps of the others. This layered approach reflects a specific lesson absorbed from decades of observing American military technology. Single-point advantages are always eventually countered, and the way to force a genuine capability crisis is to build systems where defeating any one layer exposes a platform to the remaining layers. If stealth defeats conventional radar but not quantum illumination, and quantum illumination defeats aircraft at short range but not at distance, then combining quantum detection at short range with satellite optical tracking at long range with AI-fused sensor networks in between, creates an architecture where no single stealth capability defeats all. 3 simultaneously. A report from the China Aerospace Studies Institute confirmed that PLA is simultaneously developing cognitive radar with AI-adjusted transmission, quantum radar, microwave, photon radar, and bistatic configurations using 2 separated receivers, all as part of a coherent counter-stealth program rather than isolated research projects. Like and subscribe, because the United States isn't simply waiting for Beijing to solve the problem first. What almost nobody has. Connected clearly enough is that DARPA, the Defense Advanced Research Projects Agency, launched Phase 1 of a program called Robust Quantum Sensors, or ROQS, in August 2025. This program has a specific immediate goal that goes beyond research. Take quantum sensing technology that currently exists only under carefully controlled laboratory conditions and make it survivable, reliable, and deployable on actual military hardware. The program explicitly targets ground vehicles, submarines, aircraft, and satellites as platforms for quantum sensor integration, and it uses a helicopter as the initial test environment precisely because helicopters represent the worst possible conditions for sensitive quantum instruments: strong electromagnetic fields, constant vibrations, and unpredictable gradients. Read that again, slowly. The United States government is spending real money to mount quantum sensors on a vibrating military helicopter and see what survives. That is not theoretical research, that is engineering for deployment. The core problem ROQS is trying to solve is decoherence, the process by which quantum states collapse when they interact with the environment around them. A quantum sensor works by maintaining a precisely controlled quantum state, the superposition of possibilities that gives quantum systems their measurement advantage over classical instruments. Vibration, temperature change, electromagnetic interference, and even the physical pressure of air on a sensor housing can all disrupt that state, collapsing it into a classical system that offers no measurement. Advantage over the conventional sensors already flying on military platforms today. In a laboratory, this is managed through isolation, temperature control, and carefully limited interaction with the environment. In a helicopter, flying at 150 knots through turbulent air near a contested coastline, none of those controls are available. Cue Teetrell's specific expertise in quantum control software, the algorithms that actively compensate for decoherence in real time by adjusting the quantum system's parameters faster than the environment can disrupt them, addresses this problem at the software layer rather than the hardware layer. Instead of building a better physical shield against environmental noise, it teaches the quantum system to correct itself against environmental noise as it occurs. If this approach works at the scale and speed required for a military platform, it represents the key engineering breakthrough that has kept quantum sensors in laboratories rather than aircraft for the past decade. Like and subscribe, because $24 million from DARPA to solve one company's approach to this single problem is not a casual investment. It's a bet that the solution to decoherence on military platforms is a software problem, not a physics problem. It's navigation and positioning, a quantum-enhanced inertial navigation system that functions without GPS and cannot be jammed, spoofed, or denied by any adversary. In a Pacific conflict scenario where China has spent years developing capabilities to degrade and destroy the GPS satellite constellation that most American precision weapons, aircraft systems, and ship navigation currently depend on, is military that can navigate to precisely the right location using quantum sensors that don't need any external signal, is a military that has removed one of China's most important asymmetric advantages from the board entirely. The Australian company QCTRL was among those selected for ROQS contracts in August 2025, receiving roughly $24 million in American defense funding to develop field-validated quantum sensing technologies for high-performance military vehicles. QCTRL's specific expertise is in quantum control software. The algorithms they protect quantum systems from the decoherence that destroys their precision when they're exposed to real-world vibration, temperature change, and electromagnetic interference. Solving decoherence isn't a secondary engineering challenge. It is the central unsolved problem that has kept quantum sensors confined to air-conditioned laboratory environments for the past decade. If the ROQS program successfully demonstrates sensors that can function aboard a military helicopter, the next step to submarines, satellites, and fighter aircraft becomes a matter of engineering refinement rather than fundamental physics breakthrough. Now understand what this means for China's strategic planning specifically. Beijing has spent years building what analysts call an anti-access area denial architecture, or A2AD, a layered system of missiles, radar networks, electronic warfare systems, and naval assets designed to make the Western Pacific prohibitively dangerous for U.S. forces attempting to project power into the region. The core assumption underneath China's A2AD investment is that American forces depend on GPS for precision navigation, satellite communications for command and control, and stealth aircraft for the ability to penetrate Chinese air defenses. Undermine those three pillars, and the argument goes, an American power projection in the Pacific becomes costly enough to deter. This strategy has produced enormous Chinese investment in anti-satellite weapons over the past decade. ASIT missiles, directed energy systems capable of blinding, or damaging satellites in low Earth orbit, and sophisticated GPS jamming and spoofing equipment capable of degrading positioning signals across large geographic areas. All of these programs trace their logic back to the same strategic calculation. If American precision-guided munitions can't find their targets because GPS is unavailable or unreliable, the qualitative advantage that precision weapons provide is diminished. An F-35 that can navigate stealthily but can't precisely locate its target is less valuable than the $1 trillion invested in developing and fielding it would suggest. Quantum navigation destroys the GPS dependency argument completely. An aircraft or a ship that navigates using quantum inertial systems doesn't need a single GPS signal to know exactly where it is, how fast it's moving, and where it needs to go. China's decade of investment in anti-satellite weapons, GPS jammers, and spoofing technology assumes that American forces remain dependent on a constellation of satellites that can be threatened, degraded, or destroyed. Like and subscribe, because quantum sensing potentially makes that entire class of Chinese investment irrelevant in a single technological step. The anti-submarine dimension of quantum sensing in the Pacific deserves its own analysis, because it may be the most immediately consequential. DARPA's Separate Ambience program, running from 2021 to 2025, developed quantum magnetometers for airborne platforms, specifically targeting integration onto the Navy's P-8 Poseidon Maritime Patrol aircraft by 2026. A quantum magnetometer doesn't find submarines by listening for sound, the way conventional sonar does. It detects the tiny magnetic field distortion that a metal submarine hull creates. In the surrounding seawater, a signature that cannot be turned off or reduced through acoustic quieting, because it's not acoustic at all. China has invested enormous resources into building a modern submarine fleet, with new Type 093 attack submarines and the new Hangor-class variant from Chinese-Pakistani cooperation, both designed around reducing acoustic signatures to levels that conventional sonar finds difficult to track. The quantum magnetometer deployed on a P-8 overflying. The South China Sea doesn't care how quietly a submarine is running its propulsion system. The metal is there. The magnetic field is there, and a sufficiently sensitive quantum magnetometer can detect it from altitude. Read that again slowly. China's investment in quiet submarines, built on the assumption that acoustic stealth provides protection from maritime patrol aircraft, faces a potential obsolescence event from sensors that work on completely different physical principles. The same logic that makes quantum detection a threat to aircraft stealth applies equally, and perhaps more immediately, to submarine stealth, because the magnetic signatures of submarine hulls are, if anything, larger and more persistent than the photon reflections of aircraft surfaces. The United Kingdom's Defense Science and Technology Laboratory tested portable quantum magnetometer arrays in 2025. Exercises, reporting a 70% reduction in search times compared to conventional acoustic search methods. AUKUS Pillar. 2, the technology sharing component of the Australia-UK-US partnership, explicitly includes quantum anti-submarine warfare technology in its scope, with joint testing planned across 2026. China's submarine fleet expansion, which has been one of Beijing's most significant military investments of the past decade, is premised on the assumption that the Pacific Ocean provides a volume of water large enough and opaque enough to hide submarines from adversary detection. That premise deserves re-examination in light of sensors that detect not sound but magnetic fields, not acoustic signatures but physical mass in water. But that's not even the worst part for China's planners. The CSIS analysis from November 2025 noted that the United States currently faces this entire quantum competition with fragmented investments and no coherent national strategy, with researchers in DARPA, the military services, national laboratories, academia, and industry pursuing breakthroughs independently without a unifying technical vision. That diagnosis is honest and correct, and it also describes a situation that is, by the same logic, remediable, because fragmentation in a bureaucratic system is a problem that executive direction and money can address relatively quickly compared to the underlying physics challenges. The White House issued executive orders on quantum technology in early 2025, directing federal agencies to coordinate quantum research programs and accelerate timelines for deployment of quantum technologies on defense platforms. The National Quantum Initiative, which preceded these orders, had already established a baseline of federal investment across quantum computing, communication, and sensing. Combined with the DARPA ROQS program's Phase 1 launch, The existing ONRC of sensing program that awarded $35 million in 2023 for underwater quantum networks, and the AUKUS partners' commitment to joint quantum ASW testing, the structural picture is one of a disorganized but very large and very well-funded quantum sensing enterprise, beginning to cohere around specific deployment targets. Like and subscribe, because China's mass production of the photon catcher in October 2025 was widely covered as a breakthrough for Beijing. What got far less attention was the parallel reality. By the same date, China's quantum radar program remained confined TO-controlled environments and short ranges, with fundamental physics challenges still unsolved. The photon catcher is a component. It is not a system. Assembling components into an operational system that can detect an F-22 at 100 kilometers in a real Pacific airspace environment with temperature variation, humidity, atmospheric scattering, and electromagnetic interference present at all times is a gap that engineering alone cannot bridge without additional scientific breakthroughs that haven't happened yet. The physics of this limitation are precise and not easily dismissed. Experiments conducted so far have demonstrated quantum detection advantages of roughly 20% compared to classical radar, but only in controlled laboratory settings and at very short ranges. Maintaining quantum coherence between signal and reference photons becomes exponentially more difficult over distance because atmospheric scattering and thermal noise degrade the entanglement that makes the whole system work. Quantum memory capable of storing the reference photon long enough for a long-range detection cycle remains under development. Most prototype systems still require cryogenic cooling to preserve entanglement, making them unsuitable for field deployment on any platform that isn't a specially configured laboratory vehicle. One physics review, published with a May 2026 editor's note acknowledging updated research, findings concluded that microwave quantum radar cannot achieve operationally useful detection ranges with current technology, as the maximum achievable range may be physically limited to tens of meters by fundamental constraints in the radar equation, rather than engineering limitations that could be overcome through better components. That conclusion is important and shouldn't be buried. It means China's photon catcher, impressive as it is, as a component-level manufacturing achievement, does not yet translate into an operational system that can do what Beijing's state media implied it might do: like and subscribe. Because the gap between a mass-produced component and a deployable detection system capable of finding an F-22 over the Taiwan Strait is the gap that the rest of this decade will be contested around. And both sides currently have significant unresolved problems standing between where the technology is now and where it needs to be to change the Pacific balance. The more immediately deployable side of the quantum sensing revolution isn't radar detection of aircraft at all. It's navigation that doesn't need GPS. It's magnetic detection of submarines that doesn't need acoustic signatures. It's inertial guidance for precision munitions that doesn't need external reference signals. And on every one of those applications, the United States, through programs like ROQS and Ambience and allied partnerships under AUKUS, is currently closer to field deployment than China's photon catcher is to becoming an operational aircraft detection system. But the regional implications extend well beyond a direct US-China binary. Taiwan's F-16V fleet and any future fighter acquisitions depend significantly on the ability to approach potential conflict zones without being detected early enough to be engaged at long range. Japan's Air Self-Defense Force, currently operating F-35s and co-developing the GCAP next-generation stealth fighter with the UK and Italy, has a direct interest in whether Chinese quantum radar can eventually track aircraft that its own operational planning assumes will penetrate Chinese detection layers undetected. South Korea's KF-21 Boromai program, while not a full stealth design, incorporates reduced observability features whose effectiveness against quantum detection is an open question that Seoul's defense planners are actively examining. For each of these partners, the quantum sensing competition isn't an abstract great power technology race. It's a direct determinant of whether aircraft their governments have spent billions procuring will actually survive the early hours of a conflict in the way that the operational plans built around those aircraft assume. A quantum detection breakthrough that rendered F-35 stealth partially or fully compromised would require not just a technology response, but a complete reassessment of operational doctrine, base locations, sortie planning, and the entire architecture of Pacific deterrence that the United States and its allies have spent 2 decades constructing. The Pacific military balance is being contested in laboratories right now in arguments about quantum coherence and decoherence, about cryogenic cooling requirements and room temperature alternatives, about sensor fusion architecture and the AI algorithms needed to make sense of quantum sensor output in real time. None of that sounds like the kind of decisive technology moment that changes everything overnight. It rarely does, right up until it does. The first country to field a deployable, ruggedized quantum navigation system eliminates China's GPS denial advantage in a single step. the first country to field a deployable quantum magnetomet R on maritime patrol aircraft, rewrites the strategic value of every quiet submarine in the Pacific. These are not distant possibilities. They are engineering programs in their first operational phases, funded and running right now. And that brings us back to where we started. 70 years of stealth doctrine, built on the assumption that invisibility is a solved problem, now faces the first serious physical challenge to that assumption since radar was invented. The era of uncontested stealth isn't over yet, but the physics that might end it are now in mass production in Anhui province, and the engineering required to survive real-world deployment is being tested on a vibrating helicopter somewhere over American soil.